Welcome to lecture number 5 for ECE 320, Digital Electronics, the p-n junction. Now, where we left off at the last lecture was with silicon. You have two types of silicon. I have N-type and P-type. In N-type silicon, I dope it with phosphorus, and almost all the charge carriers are electrons. In P-type silicon, I dope it with boron, and almost all the charge carriers are holes. With doping, I can build a resistor. If I take N-type and P-type silicon, put them together, I get a very unique device. It's a diode. This is a valve. If we go into Circuit Lab, one of these, here we are. The p-n junction is modeled as a diode. If I sweep the voltage, let's see if I can bring this over for you. I'm going to sweep the voltage V1 going from 0 to 0.9 volts in steps of 0.01. If I run that sweep, here's what I get. The current is basically 0 until I get to about 700 millivolts, and then it takes off. That's not linear. That's an exponential relationship, very different than a resistor. If I look at, say, this circuit, I take a 10 volt sine wave, run through a 100 ohm resistor, so the maximum current I can ever get is 10 over 100, 100 milliamps through a diode. And let's grab the ones in the lab. We use 4004 diodes. Let's simulate it. What happens to the voltage at V0 and V1? If this is a resistor, as V0 goes plus and minus, V1 goes plus and minus. By voltage division, it'll be smaller, but it'll also go plus and minus. Let's see what happens with the diode. I'm going to run this for 2 milliseconds, 2 cycles. Time steps 2 microseconds. So I have 1,000 points on the plot. You get kind of a nice plot. The blue line is the input V0. The orange line is V1. So when the voltage is negative, the output follows the input. When the voltage is positive, or actually when the voltage is above about 0.6 volts, the diode clips at about 0.7. If I plot the current, let's plot the current through the diode right here, and run it again. Now I'm getting something really strange. On this orange part, I get current flow. That's where the diode turns on. Over this part right here, the current is 0. Well, basically 0. It's minus 112 nanoamps, basically 0. Kind of a valve. For positive voltage, I get current flow. For negative voltage, it turns off. That's really unique. That's the p-n junction, that's the diode. So what I want to look at in this lecture is, why do diodes do that? Why do they behave in a way that current flows one way, but not the other? How do you model circuits that have diodes and calculate the voltages and currents? Well, a couple ways to look at it. Again, a p-n junction, current only flows in one direction, and here's the symbol for it. That's a little arrow reminding you current goes that way. Not one of these ways. Well, it goes left to right, the way it's drawn on the page. So kind of 3 ways to describe why diodes are valves. As long as one of them makes sense to you, that's all you need for this course. One way to explain it is I've got majority carriers and minority carriers. In the p-type region, there are a few holes, not very many. The number of holes is like 10 to the 5th per cubic centimeter. Number of minority carriers is like 10 to the 5th. Number of majority carriers is 10 to the 16th, like 10 to the 11th to 1 ratio. So the resistance is much, much, much less using majority carriers. There's 2 ways I can have current flow. I could have holes and electrons come together this way, or the opposite way. When holes and electrons come together, you don't get explosions, stuff like that. All that happens is a hole is a missing electron in a covalent bond. If the electron fills it, the hole disappears and the electron disappears. So I could have current flowing this way or that way. If I have current flowing using holes in the p-type region, electrons in the n-type region, current is flowing left to right. and I'm using majority carriers. Because I'm using majority carriers, there's a large number of carriers, very low resistance. On the other hand, if I try to make current go backwards, I'm using minority carriers in the N region, minority carriers in the P region. Very few carriers means very high resistance. So basically, a diode is a variable resistor, low resistance forward, high resistance backwards. That's one description. Another description. At the inside the p-type region, I have Brownian motion. Some holes go left, go right. Some holes go left, and they kind of cancel out, except at this p-n junction. At this p-n junction, some holes go right, and there just aren't any holes to replace them. So the net result is all these holes over here get swept away and wind up on the n side. Likewise for the electrons. Some are over here, well, in this region, some electrons go left, some go right, and they cancel out. That's equilibrium. Except at the p-n junction. Here some of the electrons go left, and there's nothing to replace them. So you wind up with a bunch of electrons on the left, and all these electrons are swept away. What that means is I have this region called the depletion region. This is a region with no charge carriers. If there's no charge carriers, there's no current flow. If I apply voltage backwards this way, what happens is the depletion region just gets bigger, and a bigger insulator doesn't conduct. On the other hand, if I apply voltage the other way, plus to minus this way, what happens is the depletion zone gets squeezed down to 0. Once it's gone, I conduct. That's the second way to describe it. A third way to describe it. I have all these electrons on the left side, all these holes on the right side. That's minus charges and plus charges. That creates a voltage, a potential energy barrier. It takes a little bit of energy, about 0.7 volts, to overcome it. If I have less than 0.7 volts, I don't have enough energy to overcome the potential energy barrier, and there's no current flow. More than 0.7 volts, I get current flow. So this kind of says what you should get is about 0.7 volts. If this is current and this is voltage, nothing happens, nothing happens, nothing happens, then suddenly get current flow. Okay, so it's kind of three ways to describe it. As long as one of those makes sense to you, that's good enough for this course. Just got to remember current flows P to N. And that's the symbol for diode. A little arrow reminding you current flows this way, not the other way. Some implications of this. Diodes are inherently capacitors. That is a problem when you get into high switching circuits like computers. It takes time to charge and discharge a capacitor. On computers, I don't have time. I want to do logic 1, logic 0 really quickly, like in microseconds, nanoseconds, femtoseconds. Because of that, I don't like using diodes and high switching computers. Second implication is the voltage depends upon the doping. Kind of figure if I don't have any doping, I have two pieces of silicon, there's going to be no voltage drop across them. If there is doping, I have a p-n junction, and there's a little bit of voltage to turn it on. Again, kind of like what we did before with the potential energy barrier. There's about 0.7 volts to turn on a silicon diode. If the doping is 10 to the 16th, the intrinsic carrier concentration is 1.5 times 10 to the 10th. You get about 0.7 volts across it. And the voltage depends upon the type of diode. Silicon diodes are about 0.7, germanium diodes about 0.3, red LED is about 1.9, blue LED is about 3.3. Pretty much you need a little bit of voltage to turn on a diode. Once it turns on, the voltage is almost constant. Another implication. The intrinsic carrier concentration depends upon temperature. Since the voltage across the diode depends upon the intrinsic carrier concentration, the voltage across the diode depends upon temperature, and that lets you measure temperature using a diode. Just take a diode, turn it on, measure the voltage drop. As the temperature varies, the voltage drop changes, so I can tell you what the temperature is by measuring the voltage drop across a given diode. That's one type of temperature sensor. It's a thermal diode. I can use diodes as radiation sensors. Now normally there's no current flow through a diode. If I take that PN junction, here's the P-type, here's N-type, there's a depletion zone where there's no charge carriers. If I hit that with a photon, and that creates an electron and a hole, let's call that a P for hole. What's going to happen is the electron will get swept this way, the hole will get swept that way. And the more photons that hit it, the more electrons that kick out of their covalent bond, the higher the current. So this is actually a radiation sensor. It also kind of works from duality. With an LED, something we're going to be covering a little bit later, if I apply current to an LED, I produce light. From duality, if I apply light to an LED, I produce current. So that's one way to measure light or radiation. Now to come up with the BI characteristics for a diode, it's not linear. Essentially I need about 0.7 volts to overcome the potential energy barrier. The energy for a given electron follows a gamma function. Kind of looks like this. As I increase the voltage, this curve shifts right. Or equivalently, I can take the potential energy barrier and shift it left. And on a relative basis, it's the same thing. So what you can kind of see is if the voltage is low or the potential energy barrier is really high, there's very few electrons with enough energy to overcome the potential energy barrier. I will get some electron flow, but not a lot. As I increase the voltage, or take this line and slide it left, I get more and more electrons, and then suddenly I get a whole bunch. What that means is the current flow versus voltage is exponential. It looks kind of like this. I get no current, or very, very small current, very, very small, and then suddenly the current takes off. That's modeled mathematically as the following. It's the current is some nominal current, that's the reverse saturation current, times an exponential, that's the voltage across the diode, and this is VD. This is the current through the diode. Current's related to voltage as an exponential. The reason for that -1 is when the voltage is 0, I've got to get 0. I've got to pass through the origin. So when VD is 0, e to the 0 is 1, 1 minus 1 is 0, current is 0 when voltage is 0. Going the other way around, the voltage is a log function of current. Either way you want to do it. Now these parameters, I0 and eta, are functions of the diode. For circuit lab and the diodes we have in lab, N is about 1.45. VT is Boltzmann's constant. It's 0.026 volts at 300 degrees Kelvin. And I0 is a parameter of the diode. It's essentially when the voltage is negative, this goes away. What's the current when the voltage is negative? It's called the reverse saturation current. For the diodes we're using in lab, like the 1N4004, this is I0. N is 1.45, making NVT 0.0377. That's the voltage current relationship for a diode, and that's what it looks like if you graph it. I can do that in circuit lab somewhere. There it is. If I sweep the voltage from 0 to 0.9 volts and look at the current, you get the same thing. It's basically almost no current, and then it takes off. So this creates a problem. How do you analyze circuits that have diodes? What we've been doing is writing n equations for n unknowns with linear circuits. I can then throw that in Matlab, use matrix inverse, and solve, using either current loops, voltage nodes, Well, that works for linear circuits. It doesn't work for nonlinear circuits. So how do you analyze nonlinear circuits? Well, there's a couple ways to do it. One, it still comes down to n equations, n unknowns. I've got to write n equations, n unknowns. If I had this circuit, for example, I've got two unknowns, the voltage across the diode and the current through the diode. To solve, I need two equations for two unknowns. Well, one equation is just the diode equation. This defines the diode. That's always going to be in the circuit. The second equation I can get from circuits 1. I can say that conservation of current left plus current down equals 0. Current left is VD minus 5 over 1,000. Current down is ID. Two equations, two unknowns. I could also do a current loop and say that minus 5 plus 1,000 ID plus VD equals 0. Or I could also say that 5 is equal to VD plus 1,000 ID. Any of those work. Here's my one equation. Any of these are the second equation. Two equations, two unknowns. With that, in theory, I can solve, but the problem is these are nonlinear. So, one way to do that is a graphical solution. I can take the first equation, the diode equation, and graph it. That's in red. I can take the second equation and graph it. That's in blue. That's actually called a load line. I've got this circuit right here, 1K, 5 volts. If I were to put a random resistor over here, if the resistor is infinity, the voltage is 5 and the current is 0. That's this point. If the resistance is 0, I get 5 volts over 1K, 5 milliamps, this point. That's a linear circuit. Any other resistance has to be on this load line. The solution then is where the two intersect. That's my solution to two equations, two unknowns. That's one way to do it. Second way is use Matlab and find a numerical solution. For this, we're going to use the function fminsearch. Fminsearch is a really, really useful function. It tries to find the minimum of a functional. So what I want to do is come up with a function. I'm going to guess the voltage across the diode. And if I guess it right, it returns a minimum. So what I'll do is, given the voltage, I can calculate the current through the diode, ID. I can calculate the imbalance in current. So current left plus current down should be 0. So here's I guess I did voltage. I should have 5 is equal to 1,000 ID plus VD. I'm going to change that, bring the 5 right. That should be 0. If I guess VD correctly, that'll be 0. Instead of making it 0, I'll call it an error. So if I guess wrong, I've got an imbalance in the current. Make J the error squared. What that does is if the error isn't 0, J is positive. The minimum of J is when the error is 0. The minimum of J is the voltage that makes everything balance. Now solve using fminsearch. And to kind of show you how that works, I got a lot of stuff open here. Let's take this function, maybe. So in Matlab, I did a file new and put this in Matlab. Diode 1 is not a function of Matlab. If I call it, it's going to give me an error message. I don't know what that is. Well, I'm going to create this M file and save it. Because I already did that. Called Diode 1, same name as the file. This you can't run. It's a subroutine. You can't run subroutines, but I can call it. So in the main routine, I can sit there and say, let's call Diode 1. Is the voltage across the diode 3? What it does is it takes the diode equation, the load line, takes the difference in the two, square them, and the square difference is 7 times 10 to the 54th. Saying that was a really bad guess. Is it 2 volts? Better. Is it 1 volt? somewhat better, is at 0.6 volts. Much, much better guess. fmin search will guess for you. And just for fun, this really slows it down. I'm going to have it display what's happening as I guess. To call fmin search, I call the function fmin search. I tell it what function I want to minimize. I want to minimize the function called Diode1. And what's my initial guess? See, my initial guess is 1 volt. It's then going to iterate. So here's the guess. Here's the log base 10 of the error. And eventually wound up at 0.6729. Sometimes it kicks out due to max iterations. Sometimes it kicks out because it can't find a better answer. So what I did is I said, pick up where you left off, keep going. And the net result is I got the same answer. So that's the solution. It thinks the answer is 0.6729 volts. Or 0.6730 last time I ran it. That's one way to solve two equations, two unknowns that are nonlinear. Another way to solve is to throw the circuit into CircuitLab. Now, in CircuitLab, if you click on the diodes, double click on it, maybe. These are the different diodes CircuitLab has on hand, or in this model. The one that's pretty similar to the ones we used in lab is the 4004. And here's the data for it. That's reverse saturation current. These are N for NVT. If I go into CircuitLab, and where was it? This guy, and tell it simulate. I want to look at what is the voltage and click on right here, what's the current. It'll tell me the answer is 0.665, 4.33 milliamps. So that's another way to solve. And if it went and built it in the lab, I'd come up with a third answer. So that's typical in electronics. I'm going to get a different answer every time I analyze it a different way. Matlab uses a model that's a little bit wrong. CircuitLab uses a model that's close, but it's a little bit wrong. Hardware is really what you care about. All the answers should be slightly different, again, slightly different models, but close. That's one way to check your answers. If you do it this way and 2 out of 3 are close, you know the one that's off, you did something wrong. If the hardware is off, you probably put the diode in backwards. The direction of the diode, what they look like is this. There's the line on them. That line is this line on the diode. That's the direction of current flow. And this is the anode. There's the cathode. Anode, anode, cathode. Okay, so that was easy enough. Suppose I have this circuit with 2 diodes. Now find the currents and voltages. Well, what we did before is if I have 3 nodes, I need 3 equations for 3 unknowns. In this case, I've got 3 nodes, plus I also have the current through the diode. So I've got 5 unknowns. Well, I can calculate the current through the diode if I know the voltage across it. Again, the voltage goes anode to cathode. All this diode cares about is what's the voltage anode to cathode. So for this diode, that's right there, this is VD. Its voltage is V2 minus V3. Doesn't care about the rest of the circuit. All it sees is just V2 and V3. On the second diode, anode is V3, cathode is ground, so the voltage across the diode is V3 minus 0. I now know the diode currents ID1, ID2. For the next equations, I just use voltage nodes. At node 1, these 3 currents have to add to 0. At node 2, current up plus current down equals 0. Current up is V2 minus V1 over 200. Current down is ID1. ID1 as a 1. At the third node, current up, current down, current right equals 0. Current up is minus ID1. Current down is ID2. And current right is V3 minus V1 over 300. So these are the equations that describe that circuit. On quizzes and tests, that's what I'll be asking. Write the equations. On the homework you can solve. On tests you probably can't solve. But what's important is get the equations right. If the equations are wrong, you're kind of dead in the water. If I have the right equations and I have time and Matlab, I can solve. To solve, we do kind of the same thing we did before. I'm going to guess V1, V2, V3. So first I create a function in Matlab called Diode2. Completely original name. I'll then parse it. X is a matrix. The first element means V1. The second element means V2. Third element means V3. I define IDSS and NVT. Here's the diode equations. The voltage across this diode is V2 minus V3. This diode is V3 minus 0. The node equation. These need to balance, be summed to 0. If I got it wrong, it won't be 0. So call it E1. So there's the current left, V1 minus 10 over 100. Current at the 200 ohm, 300 ohm, 400 ohm. This is the second node, current up plus current down. And the third node, minus ID1 plus ID2 plus V3 minus V1 over 300. Okay, so I created this function in Matlab called Diode2. Again, completely original name. I'm going to guess V1, V2, V3, calculate the currents of the diodes, calculate the current imbalances at the nodes, return the sum squared of the current, and just for fun, display the voltages, the log base 10 of the cost. So now in Matlab, again, this guy can't run. If I try to run it, it gives me an error message. In Matlab, I can run it. Let's try Diode 2. And I'm going to guess the voltages are 1 volt, 2 volts, 3 volts. Did I get it right? The sum squared error is 10 to the 48th, saying that was a really lousy guess. Okay, let's try 3 volts, 2 volts, 1 volt. That was better. Now the sum squared error is only 647. Is it 4 volts, 2 volts, 1 volt? A little bit better. Or let fmin search guess for you. So this will be VE equals fmin search. I want to minimize the function Diode2. And here's my initial guess. And you can see it's going to guess again, guess again. The third column is the log base 10 of the error. The more negative, the better. So it's trying. It's a little bit slow. My displaying the answers and that pause really slows it down. But it's kind of fun to see what's happening. I'm now at 10 to the minus 10. That's actually really good. 10 to the minus 11. There's your answer. 5.27 volts, 1.47.75. That's how to solve 3 equations, 3 unknowns when they're nonlinear. fmin search is actually really useful. It can solve a lot of problems. Another way to solve it. Throw it in Circuit Lab. Again, in Circuit Lab I could build a circuit. It's one of these. There it is. Here's the circuit in Circuit Lab. I can then say I want to look at what is V1, V2, 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 V3, solve. And to get an answer that's close, a little bit different. And again, that's typical in this class. The models aren't exactly the same, so the voltages won't be exactly the same, but they should get you close. If I built this and then measured the voltages, again, I should get something kind of close. So here's the handout for you. Try to write n equations for n unknowns for this circuit. And if you're watching online, just pause the video, try to write those, then we'll go over it. Okay, assuming you picked up again, let's do it this way. For the first diode, ID1 is your IDSS. Make that bigger so you can see it. Times the exponential of the voltage across the diode. Diode 1, anode to cathode, is B1 minus B2. So there's your first diode. The second diode. Its voltage, anode to cathode, is B2 minus B3. Third diode. Its voltage is B3 minus 0. Again, it's always anode to cathode. That's 3 equations. Next 3 equations would be your node equations. At node 1, these currents have to add to 0. And that would be, at node 1, the current left is V1 minus V0, less 100, plus the current down, that's just ID1, plus the current through the 400 ohm, V1 minus V2 over 400, plus the current through the 500 ohm, V1 minus V3 over 500, plus V1 over 600. That's everyone. That's got to balance. At V2, I have the current up, which is just minus ID1, current down, plus ID2, plus the current right, V2 minus V1 over 400 has to be 0. At node 3, the current up is minus ID2, current down is plus ID3, current right is V3 minus V1 over 500. That's got to be 0. So that'd be your 6 equations, 6 unknowns. Probably can't solve those by hand, but Matlab can with that search. So in summary, PN junction forms a diode. The symbol for it, we have a P and an N. The symbol is an arrow with a line. It goes anode to cathode. Current flows in the direction of the arrow. Current only flows one way. Diodes are valves. Current flows anode to cathode, but not the other way around. It takes about 0.7 volts to turn on a silicon diode. It's not exact, but ballpark about 0.7. That varies with temperature, which is one way you can actually measure temperature, measure the voltage drop across the diode. And it varies with the material and doping. The VI characteristics of a diode are highly nonlinear. It kind of looks about like this. And right about 0.7-ish, the current shoots up. And everything you did back in circuits still applies. I can still write n equations and unknowns for currents or voltages. The only challenge is they are now nonlinear equations. And that makes them really hard to solve. When you go into Circuit Lab, this is exactly what Circuit Lab's doing. When I tell it to solve, if I can find it somewhere, there it is, this guy. When I tell it to solve, there's a little bit of a pause. It took 0.21 seconds. It's iterating just like we did in fmin search, iterating, trying to find out what voltages make the currents balance. There she is. fmin search and circuit lab both work to solve these, but it's still really cumbersome, and you lose all intuition when it gets this complicated. We need a better tool. Well, a better tool does exist. That's the ideal diode model. That's the next lecture. But again, all models are imperfect. What we're doing here is the more accurate model, but it's also a whole lot harder. What I want to do is come up with a simple model that's still reasonably accurate. And stay tuned for the next lecture, and we'll get to that. That's lecture number 5 for electronics, the p-n junction.